Behind the closed doors of the world's largest factories, there are machines so vast they have to be wired directly into the national power grid, not plugged in. Wired in. And today, I am counting down the 10 biggest factory machines ever built. Number 10. The machine that eats cars for breakfast. An industrial car shredder does exactly what it sounds like. It eats cars, not slowly, not carefully. It consumes an entire vehicle in roughly 4 seconds and spits out fist-sized fragments of mixed metal on the other side. The specific machine worth knowing about here is the Linksys, operated by Sims Metal Management. It runs on a 9,200 horsepower electric motor. For context, a Formula 1 car produces around 1,000 horsepower. This thing produces 9 times that, and it doesn't race. It just chews. The motor itself weighs 40 tons, which is roughly the same as 6 adult African elephants, and the power demand is so extreme the machine had to be wired directly into the national grid to function at all. A standard industrial connection wasn't enough. The process starts with a whole car. 1.5 tons of steel, glass, plastic, rubber, and upholstery, fed into one end. Inside, a hammer mill spins at high speed. The hammers aren't blades. They're blunt, heavy, and they work by pure kinetic violence. The car simply ceases to exist. One moment it's a vehicle, the next moment it's confetti. Metal confetti, mixed with shredded plastic and foam, moving down a conveyor at speed. Then comes the sorting. The fragments pass through magnetic separators, eddy current systems, and air classifiers that pull ferrous metal from non-ferrous, copper from aluminum, recyclable from waste. It's not crude. The separation technology is precise enough that the steel coming out the other end is clean enough to go straight back into an electric arc furnace. And that's the part that's easy to miss. The shredder isn't just destroying cars. It's feeding the steel mills. The metal that goes in as a 1997 sedan comes out as rebar or sheet steel or the frame of a new vehicle. The Linksys can process 450 cars per hour. That's one car every 8 seconds running continuously around the clock. The scale of what that means in practice: a single machine of this class processes hundreds of thousands of vehicles per year. Every one of those vehicles would otherwise sit in a scrapyard, slowly leaching fluids into the ground, occupying land, doing nothing. The shredder turns that problem into raw material. It represents one of the most complete examples of industrial recycling efficiency ever built, not because of any single technical achievement, but because of what it closes. The loop from end-of-life vehicle back to usable steel used to take months, multiple facilities, and significant manual labor. The shredder collapses that into seconds. The car goes in, confetti comes out, and the metal goes back into the steel mills to become something new. That cycle runs 450 times every hour, every day, in facilities that most people drive past without knowing they exist. At number 9, China's 80,000-ton forging press. In the Sichuan province of China, there is a machine that stands roughly 10 stories tall and exists for one specific purpose: to squeeze metal into shapes that no other process on Earth can produce. It's called the 80,000-ton hydraulic forging press, and the number is not a typo: 80,000 tons of force. To put that in terms that mean something, a fully loaded Nimitz-class aircraft carrier displaces around 100,000 tons of water. This machine generates pressing force equivalent to 80% of that, focused, downward, into a die the size of a dining table. The press was completed in 2013 by the China Erzong Group in Deyang, Sichuan. It stands about 27 meters tall above the workshop floor, with a further 15 meters of structure sunk below ground, so the full height of the machine, from its deepest anchor point to its crown, is closer to 42 meters. That's roughly the height of a 14-story building. Most of it you never see, because most of it lives underground. What it makes is the reason it exists. The press produces large single-piece forgings, titanium and aluminum components for aircraft frames, turbine discs for jet engines, structural parts for rockets and submarines. These are components that cannot be welded together from smaller pieces, because a weld is always a weak point, and in aerospace and defense applications, weak points are not acceptable. The forging has to be one piece, and to make one piece at that scale, out of titanium, you need 80,000 tons pushing down on it. The process itself is not fast. A titanium billet, a rough ingot of raw metal, is heated to the point where it becomes workable, somewhere above 900 degrees Celsius for titanium alloys. Then, it's placed in the die, and the press descends. The metal flows into the shape of the die under pressure, not melted, not cast, forced. The grain structure of the metal compresses and aligns, which is what gives a forging its strength. A casting has random grain. A forging has grain that runs in the direction of the load. That difference is what makes a forged aircraft component survive forces that would split a cast one. A single pressing cycle on a component of this scale can take hours of preparation, heating, and controlled pressing. But the component that comes out, a wing spar, a bulkhead, a landing gear beam, might be something that would take weeks to produce by any alternative method if it could be produced at all. Before this press existed, China had to import large titanium forgings, primarily from Russia and Western suppliers. The strategic implication of that dependency was obvious. The 80,000-ton press ended it. China can now produce the largest structural forgings in the world domestically, on a machine that no other country currently operates at equivalent scale. The United States has large forging presses. The 50,000-ton press at Alcoa's Cleveland facility, for instance, which was itself considered extraordinary when it was built in the early 1960s as part of a government program to secure domestic forging capability. The Chinese press exceeds it by 60%. But yeah, the number that stays with you isn't the force rating, it's the geometry. A forging that emerges from this press might be 8 meters long and weigh several tons, shaped to within millimeters of its final form in a material that resists deformation at temperatures where most metals have long since given up. The press didn't bend the metal to its will. The metal had no choice. 8. The paper machine longer than an ocean liner. 428 meters. That's the length of the world's largest paper machines. And if that number doesn't land immediately, consider that the RMS Titanic was 269 meters long. These machines are longer than the Titanic by a margin that would swallow another city block. Paper machines of this scale are built by a small number of manufacturers, most notably the Finnish company Valmet, which has produced some of the largest and fastest paper-making lines ever constructed. The machines themselves aren't housed in a single building in the conventional sense. The structure is built around them, a purpose-engineered shed that exists for no other reason than to contain what's inside. The process starts with a slurry, wood pulp, chemically processed timber fiber suspended in water, arrives at the wet end of the machine at a consistency of roughly 1% fiber and 99% water. That mixture is fed onto a moving wire mesh at high speed, and the water begins to drain immediately. By the time the sheet has traveled through the forming section, it's lost most of its water content, but it's still fragile, still wet, still barely holding together. Then it enters the press section, where a series of heavy rollers squeeze out more water under mechanical pressure. And then the dryer section, a long sequence of steam-heated cylinders, sometimes more than 100 of them, arranged in rows that the paper sheet winds through continuously. The sheet enters the dryer section at around 50% moisture content and exits at around 5%. What comes out the other end is paper. Dry, continuous, moving at speed. The speed is the part that's genuinely hard to picture. Modern high-speed paper machines run at up to 120 kilometers per hour. That's motorway speed, a sheet of paper thinner than a human hair, traveling at motorway speed in a continuous unbroken ribbon for hours. The machines don't stop. Shutting one down and restarting it is a significant event, measured in lost production and restarting costs, so they run continuously for weeks or months between planned maintenance stops. The output from a single large machine running at full capacity is staggering in practical terms. A machine producing newsprint at this scale can generate enough paper in a single day to supply the print run of a major national newspaper for weeks. The finished paper is wound onto reels at the dry end, reels that can reach 3 meters in diameter and weigh up to 60 tons each. A single reel, in other words, weighs roughly the same as 9 adult male African elephants. The engineering challenge that doesn't get talked about enough is the tension management. A paper sheet traveling at 120 kilometers per hour across 400 meters of machinery through wet sections and dry sections and calendaring rolls has to be kept under precisely controlled tension the entire way. Too much tension and it breaks. Too little and it wrinkles, or wanders off the center line, or folds back on itself and jams. The machine's control systems are monitoring and adjusting tension continuously, thousands of times per second across the full width of the sheet. The width, for the record, can exceed 10 meters on the largest machines. So you have a sheet of paper 10 meters wide, 400 meters long in the sense that it spans the full machine, moving at motorway speed, under automated tension control, producing finished newsprint at a rate that makes manual papermaking look like a different species of activity entirely. It is. The first continuous papermaking machine, the Fourdrinier, was patented in 1801. The principle, a moving wire mesh carrying a fiber slurry, is the same one still in use today. What changed is everything else: the speed, the width, the automation, the chemistry of the pulp, the precision of the drying. 2 centuries of refinement, and the machine that resulted is longer than an ocean liner and never sleeps. The hottest thing on this list. Number 7. Steel arrives as a slab. It leaves as a coil. What happens in between is one of the most violent and precise industrial processes ever industrialized at scale. And it happens continuously at temperatures that make the air above the production line shimmer like a desert highway in August. A hot strip mill takes a steel slab, typically around 250 millimeters thick, weighing somewhere between 20 and 30 tons, heated to roughly 1200 degrees Celsius, and reduces it to a strip between 1.5 and 25 millimeters thick. That reduction happens through a series of rolling stands, each one a pair of massive hardened steel cylinders pressing against each other with forces measured in thousands of tons, squeezing the slab progressively thinner with each pass. The slab enters the roughing mill first. Here, the initial heavy reductions happen. The slab passes back and forth through reversing stands that knock it down from 250 millimeters to around 30 or 40 millimeters. Then it enters the finishing mill, a continuous tandem arrangement of typically 6 or 7 stands, each one reducing the strip's thickness by a controlled percentage, the strip accelerating as it gets thinner because the same volume of metal has to move faster to maintain continuity through the line. By the final finishing stand, the strip is moving at speeds that can exceed 90 kilometers per hour. A strip of steel, glowing orange, thinner than a fingernail at the thinner gauges, traveling at motorway speed across a runout table 300 meters long before it hits the coiler. The coiler winds it into a tight coil, and the coil, which can weigh up to 30 tons and reach 2 meters in diameter, is then moved to cooling bays. The total length of a modern hot strip mill, from the reheating furnaces at the entry end to the coilers at the exit, can exceed 500 meters. The reheating furnaces alone are substantial structures, walking beam furnaces that slowly advance slabs through a controlled temperature profile over the course of an hour or more, bringing the steel uniformly to rolling temperature before it enters the mill proper. What the mill produces is the foundational material of modern manufacturing. Hot-rolled coil is the raw input for cold rolling mills, which produce the sheet steel used in car body panels. It becomes the feedstock for pipe and tube mills, for structural section mills, for plate mills, producing the steel used in shipbuilding and pressure vessels. Every car body, every white goods appliance, every shipping container, every structural beam in a modern building. All of it traces back upstream to a hot strip mill somewhere. The scale of global production through these machines is difficult to frame in any single number that means something. So here's one that does. The world produces roughly 1,900,000,000 tons of crude steel per year, and the majority of that steel passes through a hot strip mill at some point in its processing. One machine type handling the majority of the world's steel output. The hot strip mill isn't one of the most important machines in manufacturing. It might simply be the most important. If you are enjoying the video, drop a like and a comment. It really does help the channel out. And stay with me. Because the next machine on this list doesn't roll steel or shred cars. It does something far slower, far larger, and far stranger, and it never, ever stops turning. The first continuous hot strip mill began operating at Butler, Pennsylvania in 1923, developed by John Butler Titus of the American Rolling Mill Company. The fundamental configuration, roughing mill, finishing train, runout table, coiler, has remained essentially unchanged for over a century. What changed is the scale, the speed, the automation, and the precision of the thickness control, which on a modern mill is accurate to within fractions of a millimeter across a strip moving at 90 kilometers per hour. A century of refinement. The same basic idea. And the steel still comes out glowing. 6. The rotary cement kiln, and it never stops. A rotary cement kiln, in its simplest description, is a very large, very long, slightly tilted metal tube that rotates slowly and continuously while burning material inside at temperatures exceeding 1,400 degrees Celsius. That description is accurate. It is also almost entirely insufficient for conveying what one of these things actually is. The largest rotary kilns in operation are around 6 meters in internal diameter and up to 200 meters long. 200 meters, about 2/3 the height of the Eiffel Tower, laid on its side, rotating. The tube itself is made from rolled steel plate and lined internally with refractory brick, because the steel shell would fail immediately at the temperatures involved without it. The whole assembly sits on a series of large steel riding rings and support rollers, and it rotates at somewhere between 1 and 4 revolutions per minute. Slow, deliberate, continuous. The slight tilt is what moves the material through. Raw meal, a finely ground mixture of limestone, clay, and other minerals, is fed into the upper end of the kiln. Gravity and rotation carry it slowly down the length of the tube toward the burner at the lower end, where a flame fed by coal, gas, or alternative fuels produces the heat. The material spends roughly 30 to 40 minutes traveling through the kiln's full length, passing through progressively hotter zones as it goes. What happens chemically during that journey is the entire point. At around 800 degrees Celsius, the limestone begins to decompose. Calcium carbonate breaks down into calcium oxide and carbon dioxide, a process called calcination. The carbon dioxide is driven off as gas. The calcium oxide continues toward the burning zone, where temperatures reach 1400 degrees Celsius or above, and the material partially melts and fuses into nodules called clinker. Clinker is the intermediate product of cement manufacture. It's dark gray, hard, and looks roughly like gravel. Ground up and mixed with gypsum, it becomes Portland cement. Portland cement is the binding agent in concrete. Concrete is the most widely used construction material on Earth by volume. More than 4 billion tons of it produced annually, which is roughly half a ton for every living person, every year. All of that concrete depends on clinker. All of that clinker comes out of a rotary kiln. A single large kiln can produce up to 10,000 tons of clinker per day. 10,000 tons, the weight of roughly 6,500 family cars every 24 hours from one rotating tube. The kiln doesn't stop to unload. Clinker falls out of the lower end continuously, drops onto a grate cooler where high-pressure air quenches it rapidly, and moves off to storage. The kiln keeps turning. The engineering challenge that defines kiln operation is thermal expansion. A 200-meter steel tube running at 1400 degrees internally expands significantly along its length as it heats up and contracts again when it cools. The support system, the riding rings, the rollers, the thrust mechanisms, has to accommodate that movement without allowing the tube to migrate too far in either direction. Kiln operators monitor axial drift continuously. If the tube walks too far toward either end of its support rollers, the consequences are severe. A kiln that derails its own support system is a significant industrial incident, so they watch it constantly. The kiln runs for months between planned maintenance stops, turning at 1 to 4 revolutions per minute, day and night, through seasons, through shift changes, through everything. Stopping it means a multi-day cooling and reheating cycle that costs significant production. The economics of cement manufacture strongly prefer a kiln that simply never stops. The first rotary cement kiln was patented by Frederick Ransom in 1885. The principle has not changed. The scale has grown by an order of magnitude, the fuel systems have evolved, the refractory linings have improved, but the rotating inclined tube, the raw meal going in one end, the clinker coming out the other, the flame at the bottom, the slow turn. All of it is recognizably the same machine Ransom described in the 1880s. 140 years later, it is still the only practical way to make cement at industrial scale. Nothing has replaced it. Nothing is close to replacing it. Number 5. The stamping press. Heartbeat of the automotive factory. Somewhere in the 1950s, automotive engineers confronted a problem that was essentially economic. A car body has roughly 400 individual pressed steel panels, and producing each one required its own dedicated press, its own operator, its own floor space. The factories were vast, labor-intensive, and slow. What they needed was a machine that could do the work of an entire production floor in a single stroke. The transfer press, and later the tandem press line, was the answer. And the scale at which modern automotive stamping operates would have been difficult to imagine from the vantage point of 1955. A large transfer press used in automotive body production today can exert forces exceeding 9,000 tons. Not 9,000 pounds, 9,000 tons, roughly equivalent to the weight of 6,000 family cars pressing down on a die the size of a large living room. The die itself is a precision machine steel tool that can weigh up to 500 tons and costs millions to produce. It's designed to produce one specific part: a car door outer panel, a roof skin, a hood, and nothing else. The press cycle is fast. A modern large panel stamping press can complete a full stroke, down, form, up, in roughly 3 to 5 seconds. That's a finished outer door panel every few seconds, dropping onto a conveyor, moving to the next operation. Blanks of flat sheet steel, pre-cut to the correct shape, are fed into the press automatically. The press descends. The blank is drawn, formed, trimmed, and flanged in a single stroke or a short sequence of strokes. What enters as a flat sheet exits as a three-dimensional body panel with compound curves, character lines, and precise edge geometry. The compound curves are not decorative. A flat panel of sheet steel has almost no structural rigidity. It flexes easily under load. A panel with compound curvature, like the curved surface of a car roof or door, is dramatically stiffer for the same material thickness. The stamping process is simultaneously forming the shape and engineering the structural performance of the panel. The press doesn't know this. It just comes down. Tandem press lines, where a series of individual presses are linked by automated transfer systems, each performing one stage of the forming operation, can stretch over 100 meters in length. A blank enters one end. It passes through 4, 5, or 6 press stations in sequence, each one adding detail or removing material. A finished, fully formed body panel exits the other end. The transfer between stations is handled by robotic arms or mechanical transfer bars moving in precise synchronization with the press strokes. The whole line operates as a single coordinated machine. The speed of a tandem line producing smaller parts, inner door panels, structural reinforcements, can reach 12 to 15 strokes per minute across all stations simultaneously. At that rate, a line running 2 shifts a day produces components by the thousands. A single automotive plant might run 4 or 5 such lines, each dedicated to a specific family of parts, all feeding the body shop where the panels are welded into a complete body shell. The die change is the operational constraint that defines stamping plant scheduling. Swapping from one part to another means removing the current die set, which can weigh hundreds of tons, and installing a new one. Modern quick die change systems have reduced this from several hours to under 10 minutes on optimized lines. 10 minutes of downtime to reconfigure a machine that weighs thousands of tons. That's not a small achievement. But yeah, the detail that stays with you isn't the force rating or the cycle time. It's the die. A stamping die for a major outer body panel is a piece of precision engineering that takes months to design, machine, and validate. It's hardened tool steel, machined to tolerances of fractions of a millimeter across a surface the size of a dining table. It produces tens of thousands of parts before it needs regrinding, hundreds of thousands before it's retired. And when a new car model replaces an old one, every die goes with it, melted down or stored or sold. The machine stays. The tooling disappears. The stamping press is the reason car bodies look the way they do. Smooth, curved, structurally coherent, produced at a rate that makes individual craftsmanship unthinkable as an alternative. Every panel on every car made in the last 70 years came out of a press like this one. 4. Continuous casting, the process that builds the world. Liquid steel poured at one end. Solid steel slab emerging from the other. In between, a machine that does something physically counterintuitive. It solidifies metal while it's still moving under controlled conditions continuously, without ever stopping to let the metal set. The continuous casting machine, or concast as it's known in the industry, replaced a process called ingot casting that dominated steelmaking for most of the industrial era. In ingot casting, liquid steel was poured into individual molds, allowed to solidify completely, stripped from the mold, and then reheated for rolling. Every step was discrete. Every step took time. The metal cooled, was reheated, cooled again. Energy was wasted at every stage, and the quality of the resulting steel was inconsistent because the solidification happened unevenly inside a static ingot. Continuous casting solved all of that, and it did it by refusing to stop. The machine begins with a ladle, a refractory-lined steel vessel holding anywhere from 100 to 300 tons of liquid steel at around 1500 degrees Celsius. The ladle sits above a tundish, which is a distribution vessel that acts as a buffer and flow controller, feeding liquid steel at a controlled rate into one or more water-cooled copper molds below it. The molds are the critical component. They're not static. They oscillate vertically, several times per second, to prevent the solidifying steel shell from sticking to the mold walls. The outer skin of the strand solidifies in the mold. The interior is still liquid. The partially solidified strand, solid on the outside, molten in the core, is then withdrawn downward and curved through a series of water spray zones and support rolls that continue the solidification process while bending the strand from vertical to horizontal. By the time the strand reaches the horizontal runout section, it's fully solid. Torch cutters then cut it into slabs of the required length, and the slabs move off to the hot strip mill, or plate mill for rolling. The whole sequence, from liquid steel entering the mold to solid slab exiting the torch cutters, can span 40 meters of vertical and curved machine height. A modern slab caster might be casting at speeds of 1 to 2 meters per minute, continuously, with the strand moving through the machine like a slow river of solidifying metal that has decided it will become a slab whether the process stops or not. The efficiency gain over ingot casting was transformative. Continuous casting eliminated the reheating step entirely, reducing energy consumption per ton of steel produced by a significant margin. It also improved yield, the percentage of liquid steel that becomes usable finished product, because continuous casting produces far less surface and internal defect than ingot casting. By the 1980s, continuous casting had largely replaced ingot casting in most major steel-producing countries. Today, more than 95% of the world's steel is continuously cast. 95% of roughly 1,900,000,000 tons per year. All of it passing through a machine that works by never stopping, never fully solidifying its product until the last possible moment, and relying on a copper mold oscillating at several cycles per second to prevent the whole thing from seizing up. The scale of individual machines is substantial. A large slab caster might have a mold width of up to 2,600 millimeters, 2.5 meters of steel strand emerging continuously from a single strand machine. Some casters run multiple strands simultaneously, each producing its own continuous slab in parallel, fed from the same tundish. A twin-strand caster doubles the output from a single ladle heat. But yeah, the detail that reframes everything else on this list is simpler than the engineering. Every entry before this one, the shredded car metal going back to the mill, the forged titanium aircraft component, the hot rolled coil feeding the stamping press, the the rebar and the concrete poured from cement made in the kiln. All of it, at some point, passed through a continuous caster. The liquid steel became a solid slab here first. Then, everything else happened. It's not the biggest machine on this list by physical dimension. It's the one that feeds everything above it. At number 3, the industrial autoclave and what it bakes. Carbon fiber doesn't arrive from the factory ready to use. It arrives as a fabric, a woven or layered textile of carbon strands, pre-impregnated with an uncured resin that holds the fibers in position but hasn't yet hardened. At room temperature, this material is flexible, almost soft. It drapes. It conforms to molds. It has almost none of the structural properties that make carbon fiber composites worth using in the first place. To become the material that builds aircraft, racing cars, and spacecraft, it has to be baked, under pressure, for hours, in an autoclave. An industrial autoclave used in aerospace manufacturing is, at its most basic, a pressure vessel with a heating system inside it. But the scale at which aerospace autoclaves operate makes that description feel inadequate. The largest autoclaves used in commercial aircraft production are roughly 6 meters in internal diameter and up to 30 meters long, wide enough to park 2 double-decker buses side by side inside, and long enough to fit a substantial section of a commercial aircraft fuselage. The Boeing 787 Dreamliner brought autoclave manufacturing to public attention because of how aggressively it uses carbon fiber composite. Roughly 50% of the aircraft's structure by weight is composite material, compared to around 12% on the 767 it partly replaced. The fuselage sections of the 787 are manufactured as single large barrel sections, rather than assembled from many smaller aluminum panels. Each barrel section is laid up from carbon fiber prepreg, placed in a mold, and then loaded into an autoclave for the cure cycle. The cure cycle is not fast. A typical aerospace composite cure runs at around 180 degrees Celsius under pressures of approximately 7 atmospheres. 7 times standard atmospheric pressure, roughly equivalent to the pressure experienced at 70 meters underwater. The cycle holds at temperature and pressure for several hours, then cools in a controlled manner before the pressure is released. The entire process for a large component can take the better part of a day. What happens inside the autoclave during that time is a chemical transformation. The resin surrounding the carbon fibers cross-links under the combined effect of heat and pressure, transitioning from a viscous liquid to a rigid thermoset solid. The pressure simultaneously compresses the layup, squeezing out any trapped air or excess resin. Voids in a cured composite are structural defects, and aerospace tolerances for void content are extremely tight. The autoclave's job is to apply heat and pressure uniformly across the entire component surface simultaneously, so the cure happens evenly throughout. The engineering challenge is the uniformity. A component 6 meters in diameter and 10 or more meters long has a very large surface area. Getting the temperature to within a few degrees of the target value across that entire surface and maintaining it there for hours requires careful design of the heating and airflow systems inside the vessel. Thermocouples are bonded directly to the component during layup, monitoring temperatures at multiple points throughout the cure. If any zone runs too hot or too cold, the cure is compromised. The pressure vessel itself is a significant piece of engineering independent of what it does. A cylinder 6 meters in diameter, 30 meters long, operating at 7 atmospheres of internal pressure, has to contain enormous forces across its walls and end closures. The end door, which has to open to load and unload components, is typically a massive flange structure with a locking ring mechanism, because a hinged door at that pressure and that diameter would require actuation forces that are impractical to manage. The door locks by rotating into engagement with the vessel flange. It's the same principle as a submarine hatch, scaled up by a factor that makes the comparison feel slightly absurd. The autoclave that cures a 787 fuselage barrel is processing a component that will eventually carry 240 passengers at 40,000 feet, pressurized to the equivalent of 6,000 feet altitude for the operational life of the aircraft, potentially 30 years of pressurization cycles. The structural integrity of that barrel depends on a cure that happened correctly, years earlier. inside a pressure vessel in a manufacturing facility. No cure record is kept from that process is ever routine. Every cycle is documented. Every thermocouple reading is archived. If a question arises about a component's structural history years into service, the cure data still exists. The autoclave bakes the material into what it needs to be. And then the aircraft is built around what came out. 2. The propeller foundry, where 100 tons becomes one piece. In the shipyards of South Korea and Japan, there are foundries that cast objects so large they require purpose-built facilities constructed around a single production capability. Not adapted, not modified, built from the ground up to do one thing: pour enough molten metal into a single mold to produce a ship's propeller in one unbroken piece. A propeller for an ultra-large container vessel, the kind that carries 20,000 or more standard shipping containers across the Pacific, can span 10 meters from blade tip to blade tip. That's roughly the wingspan of a small regional aircraft. It weighs over 100 tons, and it has to be cast as a single component, because a propeller assembled from multiple pieces would fail. The stresses involved don't allow for joints. The alloy used is typically a nickel aluminum bronze, a material chosen for its combination of strength, corrosion resistance in seawater, and resistance to cavitation erosion, which is the progressive surface damage caused by the collapse of vapor bubbles against the blade surface at high speed. The melt for a single large propeller requires furnaces capable of holding and pouring over 100 tons of liquid metal in a controlled continuous pour. Stopping mid-pour creates a cold shut, a plane of weakness where the two pores meet that will eventually become a crack under cyclic loading. So the pour happens all at once. One continuous event, moving as quickly as the mold filling rate allows, with multiple furnaces tapping simultaneously into a central ladle or directly into the mold system. The mold itself is assembled in a casting pit below the foundry floor, a sand mold of extraordinary complexity, shaped to produce not just the gross geometry of the propeller, but the precise hydrodynamic surface of each blade. The blade geometry is where the engineering becomes genuinely intricate. A ship's propeller is not a simple helical screw. Each blade has a complex three-dimensional surface with varying pitch, camber, and thickness distribution from root to tip, designed to generate thrust efficiently at the propeller's operating speed while managing cavitation, noise, and vibration. The design is produced by naval architects using computational fluid dynamics, and the resulting geometry has to be translated into a sand mold accurate enough that the cast surface requires only controlled machining to reach final tolerance, not wholesale reshaping. After casting, the propeller spends weeks in controlled cooling. Rushing the cooling of a 100-ton bronze casting risks thermal stresses that crack the component from the inside. The foundry knows this. The cooling is planned as carefully as the pour, and then the machining begins. The blade surfaces are machined on purpose-built 5-axis milling machines with working envelopes large enough to accommodate a 10-meter propeller. The tolerance requirement across each blade surface is within 2 millimeters, across 10 meters of complex curved bronze. 2 millimeters of allowable deviation across a distance 35 times the length of a standard ruler. That tolerance exists because a propeller running out of balance or with incorrect blade geometry doesn't just perform poorly. It generates vibration at the shaft frequency that propagates through the entire ship's structure, fatiguing welds, loosening fittings, and in severe cases causing structural damage to the hull over time. The balancing process after machining involves measuring the mass distribution of the finished propeller and removing material from specific locations to bring the rotational balance within specification. For a component weighing over 100 tons, the balance correction might involve removing a few kilograms from a blade tip, a correction of less than 0.01% of total mass, made to a casting that took months to produce. The finished propeller is then transported to the shipyard, a logistics operation in itself, since moving a 10-meter, 100-ton bronze component from foundry to dry dock requires specialized heavy lift vehicles, route surveys, and coordination that mirrors the kind of effort described earlier in this list for oversized industrial machinery. At the yard, it's mounted onto the propeller shaft using a hydraulic press fit. No keyway, no bolts. The taper of the shaft and the bore of the propeller hub are machined to such precise matching tolerances that the interference fit between them, achieved by hydraulically driving the propeller onto the shaft, generates enough friction to transmit the full torque of the ship's engine. That engine on an ultra-large container vessel produces around 80,000 to 100,000 horsepower, all of it transmitted through a single interference fit between a shaft and a hub. The propeller that comes out of this process will turn at roughly 80 to 100 revolutions per minute for the operational life of the ship, perhaps 25 years of continuous service, crossing oceans, running in conditions from flat calm to severe storm seas. It was cast in one pour, cooled over weeks, machined to 2mm tolerances across 10 meters, and balanced to within kilograms. If it's wrong, the ship tells you, immediately, and for as long as it runs. 1. The gantry crane. Nothing else is close. Ulsan, South Korea. On the coast, at the edge of a city of over 1 million people, sits the largest shipbuilding facility on Earth, Hyundai Heavy Industries. From above, the yard looks like a small industrial city. Dry docks, assembly halls, pipe shops, outfitting berths, a steel plate stockyard the size of several city blocks. And above all of it, moving slowly on rails, are the gantry cranes. The largest of these cranes stand approximately 130 meters tall. That's taller than the Chrysler Building's roofline before the spire. The lifting capacity of the biggest units reaches 900 tons, the equivalent of lifting roughly 600 family cars simultaneously in a single hook. The span between the crane's legs straddling the dry dock below can exceed 150 meters. The crane doesn't just work above the ship. It works above the entire dry dock, from one side to the other, with room to spare. These are not cranes in the sense most people picture. A construction tower crane lifts a few tons. A heavy lift mobile crane might manage a few hundred tons under ideal conditions. A Goliath gantry crane of the class used at Ulsan is a different category of machine entirely. A structure so large that the ships being built beneath it are assembled inside it, the way a building is assembled inside scaffolding, except the scaffolding weighs thousands of tons and moves. The construction sequence at a yard like Hyundai begins not with the ship, but with the blocks. A modern large vessel, a container ship, a supertanker, an LNG carrier, is not built as a continuous structure from keel to deck. It's built in sections called blocks, each weighing anywhere from 200 to 900 tons, fabricated in covered assembly shops away from the dock. A block might be a complete transverse section of the hull, pre-outfitted with pipework, cable trays, structural supports, and sometimes machinery, before it ever reaches the dry dock. The gantry crane's job is to lift those blocks from the transport vehicles at the dock edge and place them with precision onto the growing hull below. The placement tolerances are tight. A hull block being set onto the structure below has to align with the preceding block to within millimeters, because the structural continuity of the hull depends on those joints being correct before welding begins. A 900-ton block hanging from a crane hook 100 meters in the air, guided by workers on the hull below using hand signals and radio, positioned to within millimeters. That sequence happens dozens of times per ship, across a construction period of months. The Hyundai yard at Ulsan operates multiple dry docks simultaneously. At peak production, the yard has launched more than one ship per week. The gantry cranes make that rate possible. Without them, the block building construction method, which is the reason modern shipbuilding is as fast and cost-effective as it is, cannot function. The crane isn't a support tool for the shipbuilding process. It is the shipbuilding process. The history of the Goliath-class gantry crane in shipbuilding traces back to the post-war expansion of the Korean shipbuilding industry in the 1970s, when yards like Hyundai and Daewoo invested in infrastructure at a scale that allowed them to compete with and eventually surpass the established European and Japanese yards. The cranes were part of that investment, not incidental equipment, but a deliberate strategic commitment to a construction methodology that required them. Build the crane first, then build the ships inside it. The structural engineering of the cranes themselves is significant. A gantry crane spanning 150 meters with a 900-ton lifting capacity has to manage the deflection of its own bridge girder under load. A steel beam of that span will deflect measurably under 900 tons, and that deflection has to be accounted for in the crane's geometry and control systems. The travel mechanisms, the bogies running on the dockside rails, distribute the crane's own weight, which runs to several thousand tons across enough axles to keep the rail and foundation loads within manageable limits. Maintenance on a structure of this scale is continuous and never fully complete. By the time a full inspection cycle of the crane structure, mechanisms, and electrical systems has been completed, the earliest inspected sections are due again. The crane doesn't stop working while this happens. Maintenance is scheduled around the lifting program, not the other way around. So, here's where this list lands. Every machine on it, the shredder, the forging press, the paper machine, the hot strip mill, the kiln, the stamping press, the caster, the autoclave, the propeller foundry, produces something, a product, a material, a component. The gantry crane produces none of those things. What it produces is the ship that carries all of them, the container vessel that moves the steel coil, the cement, the finished cars, the aircraft components across the oceans. The crane builds the machine that moves the world's goods, and it does it by being the biggest factory machine on the planet. By any physical measure, height, span, lifting capacity, structural mass, nothing built under a roof comes